For this homework, it looks like we're taking a look now at directed graphs. The first problem asks us to give an algorithm that takes as input a directed graph with positive edge lengths and returns the length of the shortest cycle in the graph. If the graph is acyclic, so if it doesn't have any cycles, we need to say so and obviously return that there's no shortest cycle. Your algorithm should take at most O of nm log n, where n is the number of vertices and m is the number of edges. Okay, taking a look at this, it appears that we likely want to use Dijkstra's algorithm to first find all of the shortest paths in this graph. If we do Dijkstra's starting at node 1, at the very first one, we would find the shortest distance from 1 to every other node in this little sample graph here. We'd find the shortest distance from 1 to 2, and from 1 to 3, and so on and so forth for all of these distances. Then we can take a look and see which of these vertices have edges that lead back to 1. So taking a look here at all of the shortest distances we calculated, we would also check our adjacency list and check which of them happen to go back into the vertex we started at. In this case, it would be 3 and 5. Then we just look up the distance for 3 to 1 and 5 to 1, and we would add that to their distance to get to that node from 1. In this case, let's say all of our edges have a cost of 1. Our distance to get to 3 would be a total of 2. So our distance from 1 to 3 equals 2. And our edge cost from 3 to 1 is also 1. So our edge from 3 to 1 is also equal to 1. We'd combine this, add these two together, and we would end up getting 3 as the length of this particular cycle. The other cycle here, we would then grab our 1 to 5 distance, so our distance from 1 to 5, and we would add the edge cost associated of going from 5 to 1 from our adjacency list. And 1, 2, 3, 4. This would have a distance of 4 when we calculate it using Dijkstra's. And we do a simple lookup to find the edge cost from 5 to 1. And again, I'm saying it's just 1 in all these cases. That would give us 4 plus 1 equals 5. And we would determine that this cycle has a length of 5, and this one has a length of 3. In this case, by running Dijkstra's, which has a runtime of n plus m log n, and then doing a simple quick analysis of whichever edges in our adjacency matrix happen to connect with the original one, we were then able to find all of these cycles that 1 is a part of. Now, how did we know to pick 1? We might have ended up picking 7, and if we picked 7 to start out with, we wouldn't have found any cycles, and we would have said, oh hey, this graph doesn't have any cycles. So that means we need to repeat this process for each of the vertices in our graph. We need to run Dijkstra's and then do this simple extra check at the end where we go through the adjacency list and add any of the distances to the edge lengths if they happen to reconnect back into our starting node. That means that we could potentially have to do Dijkstra's a total of n times. We might have to do it for every vertex, which would end up giving us n times our runtime of Dijkstra's, giving us, we'd have our n squared plus n m log n. And I assume they're probably okay with this runtime because you match the nm log n, and this is likely to be the dominating factor if you have a significant number of edges, which is quite likely, because if you happen to have a whole bunch of extra vertices, then you don't need to do any of the checks for those particular ones if they aren't associated with edges. And so it's quite likely that this would be the dominating factor, so I assume they would be okay with this, but you might want to have a quick question to double check. But in general, for this one, you'd simply run Dijkstra's on every vertex, and then you check any of their edges that lead back to themselves, add the distance to get to them to the distance to get back, and whichever one is smallest you record as the smallest cycle associated with that edge. You do it for all of them and you will necessarily get the shortest cycle. And obviously if you can't find any, you would just return you can't find any. Okay, now the next one here, let me clean this up so we have space. Okay, using our same little cycle, let's take a look at this one. Okay, you are given a strongly connected directed graph, G of VE, with positive edge weights along with a particular vertex, V. Give an efficient algorithm, they don't specify, they say efficient, all right, for finding the lengths of shortest paths between all pairs of vertices with one restriction, that these paths must pass through V of 0. All right, so this one's interesting. Let's say, in our case here, we have to pass through 6. So node 6 is our V0, and we want to know the shortest paths between every single pair of vertices. So from 1 to 7, from 7 to 4 if it exists, from 3 to 1, every single possible combination. So we need to find essentially n squared different paths. And so to do this, we need to think of a semi-efficient algorithm to do it. And they have to additionally have the complexity if they have to go through this particular vertex. And to find the shortest path for that, there's sort of two parts. First, we have to see the shortest path to get to 6, because we have to go through it. And then we kind of want the shortest path from 6 to whatever that node is. So if we want the shortest path from 1 to 4 that passes through 6, it's going to be the shortest path to 6 plus the shortest path from 6 to 4. So, and same idea for 2. To get from 2 to 4, passing through 6, we'll want the shortest path to 6 plus the shortest path from 6 to 4. And you can see in all of these we're repeating the path from 6 to whatever the destination node is. The path from 1 to 6 changes, but the 6 to whatever destination node is always the same. So the second half of all of these distance calculations is always simply going to be 6 to whatever our final node is. That means that if we run Dijkstra's on 6, we'll find its shortest path to every single node. So we'll end up with we'll have a little chart here with 6's distance to 1, 6's distance to 2, 6's distance to 3, 4, 5, and 7. Now, anytime we want to go from one node to any of these, we would simply add whatever this distance cost is that's associated with 6 to that destination. Then we just have to figure out the first part of how to get from all of these different nodes to 6. And this second half we did using Dijkstra's, so let's note the runtime of that. That, again, would be the n plus m log n. So this is our runtime so far. We did Dijkstra's one time for 6 to get to every other node. Now, what we could do is we could run Dijkstra's for every single other node and see its shortest path to 6, but that's not entirely efficient. That probably wouldn't pass the sniff test of being an efficient algorithm. One trick we could do, though, is what if we reversed all of these edges? If we reversed all of these edges, and so now, instead of this edge going from 1 to 2, it goes from 2 to 1. This one, instead of going from 2 to 6, goes to 6 to 2. Now, our path from 1 to 6 is actually going to be equal to our path from 6 to 1. So if we reverse every single edge in this graph, and then do Dijkstra's again on 6, it would find the shortest path from all of the other nodes to 6. Hopefully that makes sense. Normally we'd have to do Dijkstra's from every other node, but if we reverse all of the edges and do Dijkstra's again on 6, it'll do it backwards, and that'll tell us the shortest path from 6 to all of our other ones going backwards. So we only actually have to do Dijkstra's twice. First, we run it to find the shortest distance from 6 to all of the other nodes. Then, we reverse all of our edges, which I guess would take e time, because we have to go through all of our edges and fix and swap them. We run Dijkstra's again, giving us another nm log n. And this would be our total runtime. We do one operation here for n plus m log n, one operation basically of e to swap all of our edges to be opposite directions. Then we run Dijkstra's again, and we get this runtime again. So our total runtime, the e will be completely inconsequential, will be simply two Dijkstra's essentially, which, since 2 is a constant, it would be discarded, and we would have a total runtime of just n plus m log n, because we were able to do Dijkstra's two times, a constant number of times, instead of having to do it n number of times like in our previous one. And I would consider that a fairly efficient algorithm. You just have to think of the trick of reversing all of the edges so that you don't have to do Dijkstra's on every other single node. Because we only really care about paths to 6. We do it forward and then reverse everything and do it backwards, and we get all the information we need. Because we don't really need to know the shortest path from 1 to 3. We want to know the shortest path from 1 to 6 and from 6 to 3. Okay, now exercise 3. Let's clear this out again real quick. Actually, I'll draw a new graph for this one. Okay, all right. So the following statements may be true or they may not be. In each case, prove it or give a counterexample. We need to assume that it is undirected and connected. Okay. That means that you're never going to have a node that's just chilling out here, not connected to the graph. So let's draw a quick little simple undirected connected graph. All right. Let's draw a lot of nice little connecting lines here. All right. If E is an edge whose weight is less than the weight of every other edge, E is in some minimum spanning tree. All right, so let's look at an example of that. Let's say, this is 3, this is 4, 2, 5. That is a horrible 5. 3, 1, and 7. And for our minimum spanning tree, let's say let me grab another color to denote this. Let's say we pick this one, this one. We need to grab this 3. Let's take this nice short 4 actually. Let's do this path here and this one here. All right, we've got a nice little minimum spanning tree. It connects all of our nodes. And we need to prove that if there's an edge whose weight is less than the weight of every other edge, it has to be part of some minimum spanning tree. So in the case here, does this 1 have to be part of this minimum spanning tree? Well, if I swapped this 1 with any other edge, so if I swap it with, let's say, the 7, I have 7 now actually. So instead of that 1, I have a 7, and it's still a spanning tree. It connects all of the nodes, but it has a greater cost. And any edge I add that will connect this 3 to our graph. If I can't pick this 1, I have to pick either the 5, the 4, or the 7. Any of them that I pick is going to give us a larger total, because our minimum spanning trees always want to minimize. They want to have the smallest total cost of all edges. So they want to have a smallest total cost, and they also need to connect all edges. And if I have to use this 1, because if I use any of the other ones, I get a higher value. And in order to prove that, let's assume that we aren't using the 1. Let's say we are using this 4. That means if this currently is a spanning tree, if we insert this 1 as an edge, we will create a cycle. Because if it was a minimum spanning tree, it means every edge is connected to our tree. So adding in a single additional edge will create a cycle in the graph. When we do that, that means we can remove any edge from that cycle and we'll still have a minimum spanning tree. We can get rid of any edge that's a part of the cycle we created and have a minimum spanning tree that still works. We could get rid of this 4, and we have a minimum spanning tree. We've got the 1. We've got all 5 of the nodes still connected. We could have gotten rid of this one, and again, we still have a minimum spanning tree. So in that simple case, we can see if we had a minimum spanning tree and there was some other smaller edge, we would improve the value. We would have a smaller value overall by grabbing it and deleting the largest path length in the cycle that we created by adding that edge length. So it has to be used. Okay, hopefully that made sense. Now the next one here, if G has more than V minus 1 edges and there is a unique heaviest edge, then this edge cannot be part of the minimum spanning tree. All right, that one doesn't feel true to me. Let's see here. Let's say we've got this augmented a bit, and we've got this node over here, 8, and it's got a big old 10 here. And we have more than V minus 1 edges, so right here we've got 6. Actually, instead of calling this 8, let's call this 6, just so we can keep track of the number of vertices we have. All right, it's got an edge length of 10. And in this example, we've got 6 vertices. And actually, I should write our number of vertices is 6, and our number of edges is 1, 2, 3, 4, 5, 6, 7, 8. Our number of edges is 8. And we've got more than V minus 1 edges. We've got more than 5 edges. But to have a minimum spanning tree, we have to include this one, because there's no other way to connect to 6. So our minimum spanning tree would be this one here, and we have to have this line. So it's the unique heaviest edge, but we have no choice, and it is part of the smallest tree. So the second one is false. That is not true. We have this counterexample here. Our first one, pretty sure true, given our proof for creating a cycle and then removing the largest edge. I'll write a little note here. Create cycle, remove longest. That is terrible handwriting. Remove longest edge. Okay. Now, our next one, 3. The shortest paths between two vertices is necessarily part of some minimum spanning tree. Okay, the shortest path between two vertices is necessarily part of some minimum spanning tree. This one's interesting. Let's take a look at the graph here. In this case, we've got the shortest distance from 3 to 5, and that one obviously is part of it. And let's see, how could we make this graph a little more complicated? So we might have, let's see, let's add a 7 over here and an 8 over here. Let's add a few more nice edges. And let's say the distance between 7 and 8 is 1. It's the shortest distance between two vertices. Actually, that's really small. Let's make it like 4. It's the shortest path between these two vertices. And in this one, we'll make this 5, and this one also 5. And for fun, this one 5 too. So, looking at here with our minimum spanning tree, we would, we would grab this 5 and this 4. And that would continue to have our minimum. So in this case, it does look like we're gravitating towards the shorter edges. And so let's look at the wording on this again. The shortest paths between two vertices is necessarily part of some minimum spanning tree. So the shortest path from 1 to 2 is 2 as part of a tree. The shortest path from 1 to 3 is 4, but that's not necessarily part of this tree. Oh, let me get rid of this line actually. If I retained, I need to get rid of this line. If I retain this line actually, it breaks our little 10 thing. We don't actually need this. And get rid of this one too. Because we want to keep that for posterity's sake. All right, back to this tree. But anyways, I think we did serendipitously create a counter example here, because the shortest path from 1 to 3 is 4, but adding 4 here creates a larger tree, because we don't really care so much about overall shortest paths to nodes. We need to really visit all of the nodes. So taking this direct path to 3, even though it's shorter, actually gives us a larger overall spanning tree. And you can see that because if we took this one, it would mean we would not have taken this 2, and we would have a larger overall cost. So even though this is the shortest path from 1 to 3, going down this 4, it's not part of our minimum spanning tree. We would have increased the overall cost by taking it. So this would be false, and we have another counter example here, where the shortest path between two nodes isn't necessarily going to be part of a minimum spanning tree. Okay, I think that covers all of them. Hopefully this helps. Let me know if you have any questions, and have a good day.